Linear regression is built on a specific objective, finding an unbiased estimator that minimizes the mean squared error between our predictions and reality. Take 10 points of a pure sine wave corrupted by Gaussian noise. A straight line underfits this wave. A third-degree polynomial bends perfectly to capture the underlying signal, but a ninth-degree polynomial fails catastrophically, warping violently to thread through every single noisy dot. With too much mathematical capacity, the model stops learning the general trend and begins memorizing the random noise. This is overfitting, the total destruction of the model's ability to generalize. To diagnose this behavior, we have to look at the weights driving the curve. When we give a model 9 degrees of freedom for only 10 data points, the underlying matrix operations become numerically unstable, forcing coefficients to explode. Looking at the weights for our 9th-degree model, the magnitude is staggering. To force those wild oscillations, the math has assigned values in the hundreds of thousands to individual features. These massive weights create a high-variance model. Because multipliers are so large, tiny input fluctuations cause massive swings in output. Watch. Nudging a single observation causes the entire curve to snap into a completely different, unrecognizable shape. We can mitigate this by adding significantly more observations, a process called data augmentation, to drown out the noise. But in the real world, data is rarely infinite. Since we cannot always expand our datasets, minimizing training error alone is an insufficient strategy. We need a mathematical way to actively restrict the model's capacity and prevent these weights from exploding. The true test of any model is its performance on data it has never seen, a metric we call test loss. As model complexity increases, training loss drops towards zero, but test loss dips to an optimal point before sharply spiking. On the left, both error rates are high from underfitting. On the right, they diverge as the model overfits. Our goal is to hit the exact bottom of that test loss curve. To get there, we must move beyond simple error minimization and adopt a regularized loss function. A regularized loss function splits our objective into two competing forces: a data loss to fit observations, and a model penalty to keep weights small. Ridge regression implements this using an L2 penalty, which is based on the squared Euclidean norm of the weight vector. Elliptical error contours radiate outward from the unregularized lowest error solution. The L2 penalty introduces a strict geometric boundary, a circle at the origin. The algorithm expands the contours until they tangentially touch the circle, revealing our new stable solution. Mathematically, this L2 constraint adds a diagonal identity matrix to the normal equations. This ensures the system is always invertible, providing a stable solution even when the data is redundant or the features are highly correlated. By forcing the model to respect this boundary, ridge regression trades minor training accuracy for weights that are stable and resistant to high-variance explosions. LASSO regression takes a different approach, using an L1 penalty based on the absolute sum of the weights. Shifting to absolute values fundamentally changes the constraint's geometry. The smooth circle morphs into a diamond with sharp corners. As the elliptical error contours expand, they mathematically strike one of these sharp corners first. When the solution hits a corner on an axis, the weights for all other features are forced to be exactly zero. LASSO becomes an automatic feature selector. It doesn't just make weights smaller, it literally deletes less important variables, driving their influence to zero. Both methods rely on a hyperparameter called lambda. This is the dial that controls the size of our geometric constraint. Because the training math will always try to set the penalty to zero to minimize error, we cannot let the model learn lambda during the initial training phase. Instead, we find the optimal lambda through k-fold cross-validation. We split data into 5 segments, using 4 for training and 1 for validation, rotating the holdout block to find the lowest average error across all permutations. At the extreme limit of this process, known as leave one out cross-validation, we hold out just a single data point at a time. This process provides the empirical evidence we need to set our geometric constraint at the precise size that maximizes out-of-sample accuracy. Every time we minimize the sum of squared errors, we are making a specific probabilistic bet. We are performing maximum likelihood estimation, assuming the noise in our data follows a zero-mean Gaussian distribution. But we can go further by shifting to maximum a posteriori, or MAP, estimation. This approach introduces the prior, a mathematical assumption about how the world works, established before the model sees data. Our prior assumption is that extreme, exploding weights are fundamentally improbable. We assume a priori that weights cluster around zero, following a Gaussian bell curve. In the MAP framework, we no longer ask what fits the data best. We ask what is the most probable truth, balancing our noisy observations against our prior beliefs. When we combine the likelihood of our data with our zero-mean Gaussian prior, we produce a single complex equation. By taking the negative log, the exponents drop down and the constants vanish. The complex probability multiplication simplifies directly into the ridge regression objective.